Complex Numbers by me, Ion Q, for my Educere Capstone project. Complex numbers. Despite complex numbers being a pretty vast topic with an interesting history and thought-provoking properties, one may not understand just how important they are without truly knowing what complex numbers really are. To start, we need to answer the question, what are complex numbers? Well, complex numbers are the solution to previously impossible problems. Cubic equations could now be solved using complex numbers. The fundamental theorem of algebra was secured as a fundamental theorem, and solving algebraic problems became a lot easier. Now what this means is that cubic equations that had complex roots or complex parts when solving for the simpler form x cubed plus px plus q equals 0 from ax cubed plus bx squared plus cx plus d equals 0, as solved by mathematicians like Leonardo da Pisa, the outputs may have been complex, but when inputted for p and q, real number solutions would be found. Now, let's move on to the properties of a complex number. All right. Now, multiplying any number by I rotates it 90 degrees in the complex plane. Complex numbers can easily be written in terms of E through Euler's formula and identity. Taking I to the nth degree cycles between I, -1, -I, and 1 in that order. Multiplying two complex numbers together results in another complex number. Now, these are all very interesting properties, but let's focus in on taking I to nth degrees. Well, taking I to the first degree remains it as I, because taking anything to the first degree remains it as it is. Taking I to the second degree is essentially squaring the square root of -1, of which you get -1. Taking I to the third power is like multiplying the square of the square root of -1 by I, thus you get -I. And then you get 1 by squaring the square root of -1 twice, or multiplying the square root of the square of the square root of -1 times the square of the square root of -1, of which you get 1. Now, the history of complex numbers involved hundreds of people throughout hundreds of years, but let's focus in on the 6 most important people, and they include Al-Khwarizmi, Leonardo da Pisa, René Descartes, Leonhard Euler, Caspar Wessel, and William Rowan Hamilton. Now, Al-Khwarizmi, he helped form the basis of algebra, introduced quadratic problem solving, and dedicated his work to Caliph Harun al-Rashid in part of the Baghdad House of Wisdom in the 13th century. Now, he was really the first person who combined geometry and used geometry to solve complex equations, really forming the basis of algebra throughout his life. Now, he introduced the problem of solving for cubic root equations, which I mentioned earlier, but I'll state again: ax cubed plus bx squared plus cx plus d equals 0 into the form x cubed plus px plus q. And Leonardo da Pisa, when this problem was shown to him, although he was able to solve it, the solution puzzled him a bit. Now, he built on Al-Khwarizmi's work by solving for a depressed cubic equation, but the problem was that the solution allowed for negative root outputs. Going with this output, you would get a real number solution to the initial problem, but it was in negative roots. This puzzled Leonardo da Pisa, and it also puzzled René Descartes, where he coined the term imaginary with geometric impossibility, where it was impossible to exist in our real number world. Now, his work, La Géométrie, includes his application of algebra to geometry, of which we now have Cartesian geometry. Now, René Descartes is quoted as saying, "For any equation, one can imagine as many roots as its degree would suggest, but in many cases no quantity exists which corresponds to what one imagines." Now, this was before the fundamental theorem of algebra was secured as a fundamental theorem, and with the introduction of complex numbers, soon people began to realize that this could function as a real number, of which we move on to Leonhard Euler. He introduced the notation of I equals the square root of -1 and visualized complex numbers as points with rectangular coordinates. He helped define the complex plane. He identified the complex exponential and proved the identity e to the I pi equals the cosine of theta plus I sine of theta, leading to Euler's theorem, or the most famous equation of all time, e to the I pi equals -1. Now, Capsar-Wessel used what we today call vectors. He used the geometric addition of vectors and defined multiplication of vectors in terms of what we today call adding the polar angles and multiplying the magnitude. This built off of Leonhard Euler's work, of which he used the e to the I pi, or cosine of theta plus I sine of theta, to describe complex numbers in the complex plane. But Wessel's works pushed ahead and also included the real numbers, leading to vectors. Fun fact about Capsar-Wessel: his paper on these vectors was so well received that it was the first to be inducted into the Royal Society without Wessel even being in the society at the time. Now on to William Rowan Hamilton. He defined ordered pairs of real numbers A, B to be a couple. He defined addition and multiplication of said couples and ended up being one of the first algebraic definitions of complex numbers. Now let's move on to the field revolutionized by complex numbers. All right. So the fields that we have nth degree polynomials, complex analysis, and AC circuit analysis. Nth degree polynomials. Before the acceptance of complex numbers, cubic or any other function higher than the first degree were much harder to solve for their roots. Most functions always have at least one real root, but the other roots of the function defined by the highest nth degree could be complex, leading to new interpretations of functions and problems. Also leads to the concept of complex functions and complex inputs in real functions. Now moving on to this idea that polynomials with complex inputs can have complex outputs, or can have complex outputs without real inputs. With real inputs was very puzzling, which helped spur the growth of a new field of mathematics called complex analysis. Now, this branch of mathematics investigates polymorphic functions, which is particularly confirmed with analytic functions of a complex variable. The entire field simply would not exist without complex numbers, and this contributes to the AC circuit analysis, of which we will go over shortly. Complex numbers simplify many different concepts, and that isn't more present in AC circuit analysis. The two directions of an AC current can be easily modeled and described using sine and cosine, combined into one expression using Euler's formula. As seen in the diagram, the voltage shows a sine wave, and of which alternating current rapidly swaps back and forth. You could easily describe this motion using complex numbers. And that is all. Thank you for watching.